All right.
Hey guys, can you hear me?
I don't know if you can hear me or not.
Yep, I can hear both of you.
Okay, great.
Condition.
Well, I think it's 2 p.m., so we can go ahead and start. Good afternoon. Welcome to our monthly webinar for the Transportation Infrastructure Precast Innovation Center. For those who don't know me yet, my name is Bassem Andrawes, and I'm a professor here in the Department of Civil and Environmental Engineering at the University of Illinois at Urbana-Champaign. I'm also the director of TRANS-IPIC, and I'll be moderating the webinar today. First, I would like to maybe congratulate everyone on ending the semester. I hope that we had a very good end of the academic year. And we had a fantastic workshop, honestly, last month. I enjoyed seeing everyone there in person. And I wish you have a great time this summer. And looking forward to working with you over the summer and so many activities and stuff that we're going to be discussing over the next couple of months. Before we go ahead and start introducing our speakers for the webinar, I would like to maybe start with sharing a few comments about the planning for the next year workshop. We want to build on the momentum we had from this year workshop, obviously. So we're in the process of now collecting information and collecting feedback from whoever attended the workshop and primarily you guys on how did it go, what did you think we could have done better, so we can keep improving it for the next year. Roughly, we're shooting around the same time for the workshop next year, so you will be hearing from us hopefully soon about the final dates for next year, so you can, put it in your schedule and calendar. Also, I think Chris is in the process of working now with the PIs to schedule our next webinar next month. That's going to be in June. We're targeting some time in the middle of the month or so. We're going to let you know more exactly when that date is going to be, and we will share this with you. Also, last thing I want to point out is that, of course, with the summer starting, we're expecting that all 5 campuses will be holding some education activities. And I would encourage you all to, if you are participating in any of these summer activities and your research with TRANS-IPIC is going to be highlighted in these activities, that you would let us know about these news and share it with us. And usually, it's very exciting for us to see that our research in the center is being used and the knowledge is being transferred to especially younger generations, whether through K through 12 or undergraduate researchers that you're hosting in your campuses through different activities over the summer. So please feel free to contact Chris with any information that you may have about these activities that's ongoing in your on your campuses. With that said, I don't want to take more of our time here. We're having 2 very exciting topics today, very futuristic, very visionary topics that we're going to be having today. The first one is about digital twin models and how we can use this new technology for asset management, transportation asset management. And the other one is about new type of smart materials, shape memory polymers. Maybe some of you are a little bit more familiar with shape memory alloys. These are similar, but they are polymeric materials. And we're going to learn today a little bit about them and how we can use them in transportation infrastructure. So I will start with introducing the first speaker, Professor Vlad Kindratenko from the University of Illinois. Professor Kindratenko is an assistant director with the National Center for Supercomputing Applications and CSA. Excellent center we have here at UIUC, where he serves as the director of the Center for AI Innovation. He is also an adjunct associate professor with the ECE department and the research associate professor with the CS department at UIUC. His research interests include high-performance computing, special purpose computing architectures, cloud computing, and machine learning systems and applications. Without any further delay, please, Vlad, you can go ahead and take the mic from me.
Yeah, thank you very much for the introduction. Can you see my screen?
Yes.
Okay. All right. Yeah. So welcome. Thank you very much for coming for this presentation. So my name is Vlad Kindratenko. I work at NCSA, as Professor Andreas mentioned it. And so this project is on designing and implementing digital twin models for continuous monitoring and performance prediction of precast concrete bridges. And this is really closely related to the work which otherwise is typically carried out in these high performance computing centers, where we are interested in running these complex simulation models on complex systems, on complex computer systems. I should point out that this is a joint effort. So Professor Andrawes is also a co-principal investigator for this project. And we have a group of very capable and talented students who have been doing quite a bit of work. I should point out specifically Wentao Yao, who works with digital twin models. Dashina from Professor Andreas' group, who works with actual bridges and actual physical modeling and simulation. And also Tasho Mandor, who helped quite a bit with modeling, and also Anu Kwon, who is another student who worked on helping with building the simulations and bringing them into the digital twin models setup. And also Arslan Khan. Arslan is a new postdoc in Professor Andreas' group, and Arslan came just recently, but he really became a very sort of integral part of this project. He is very knowledgeable and helps students quite a bit to do what they're supposed to do.
I don't know.
Okay, so when we proposed this project, these were kind of our overarching goals. One of them was to design and validate a digital twin model of a precast concrete bridge structure, and also subsequently integrate this model with sensor data which is coming from the real world. And we had some ideas about where that sensor data might be coming from and what we can do with this. But the overarching idea was to merge these two things. And then another idea that we had was that we also wanted to play with this new platform developed by NVIDIA called Rebars. We heard a lot about capabilities of this platform to enable to build digital twin models for very complex processes and systems. And we wanted to investigate how exactly this will work, and if there are any advantages or benefits of this platform compared to what other tools are out there that are traditionally used in this space. So our research plan consisted of this essentially three main topics or directions. One of them was essentially to build a digital model. We wanted to explore how to use technical drawings and any sort of documentation available there to very quickly build models. And the key idea here was that because these bridges are built from precast parts, that there must be some sort of standard set of these precast parts that we can implement, and then we can rapidly assemble real bridges from them. Another item on the research plan was how to use NVIDIA Omniverse platform. So how we can bring this precast components into this environment, and how we can rapidly assemble something from them, and also how we can connect it to external world. And presumably Omniverse environment was supposed to give us the ability to connect with data coming from the real bridges, as well as potentially data coming from simulations or observations of other kinds. And of course, the bridge analysis and simulation is using real-time data. So once this platform is set up, once we develop all these building blocks, how we really link it together with the environmental data, with the data available in the databases, with the simulation data, and how we can build basically a data-driven digital twin model such that it really reflects the real bridge, real bridge structures. So this was the overarching plan. Few words about the digital twins. So a digital twin model is a digital representation that simulates a physical object throughout its life cycle. So given a real building or given a real bridge or given a real object, we build a virtual model. This model would have to have sort of similar appearance in some sort of a virtual world, but more importantly, it would behave in the same way as a real object. If something happens to the real object, it would be reflected on the digital twin model so that we can observe it inside of our virtual environment without the need actually to go and inspect the real bridge or real object. And so in the context of bridge monitoring, the digital twin includes basically virtual model that reflects the real-time data of the bridge's physical structures. If there are some sensors that measure something about the bridge, we want the sensors to be reflected, these measurements to be reflected in our digital twin model, and at least the data be examined on the digital twin model. But better yet, if the data can drive the sort of evolution of that model. A few words about the Omniverse. I already mentioned it why we wanted to use Omniverse. This is a new technology that was recently developed by NVIDIA, and it really capitalizes on the best GPU hardware that is available at NCSA in particular. But more importantly, the platform was originally designed as a platform for building digital twin models for all kinds of purposes. The most important part that what it has is the ability to build these plugins that enable to bring in external data, that enable to connect data feeds with the virtual models, that enable to direct the changes or apply changes to the virtual models in response to the real data. And this not only real data, but these plugins could also connect to simulations, very accurate physics-based simulations that can also be reflected in this environment and so on. And so that's what's special about this platform. That is kind of an emerging platform in this field. Okay, so let's talk about our plan. So and then the work that we have done as part of that plan. So we started with these drawings that look like this. We got a whole collection of bridge drawings that look like that, and so we spent some time trying to understand what they are. But at the end of the day, all these precast concrete bridges are built out of some sort of well-defined construction pieces, which are built some concrete is poured somewhere else, but they are brought in place at the time of the bridge construction. So these are examples of basic beam components, which we model it based on these drawings. So we have to build these models, obviously, but once they are built, we can actually then go and assemble them in our virtual environment to build one or another bridge. So we started with manually building this bridge, where we also applied all this texture and just to make it to look pretty. But at the end of the day, our goal is to be able to programmatically build these bridges. So for example, when we can go to a database and realize that that database tells us that this bridge consists of so many beams of that size, and they are arranged in this particular configuration, and we want to be able to read that information and programmatically on the fly build.
Unless you really want. Okay, send me an email. We can see.
Yeah, and so we built the plugin to Omniverse that enables to go and query a database with information about bridges, and then we can programmatically pick a bridge, and that the actual geometry of that bridge will be assembled on the fly inside this virtual environment. And so that's what we were able to accomplish with the help of Omniverse environment, just by building these plugins that can read databases and sample bridges. So once we've done that, we also started to look at how we can incorporate data from other databases. For example, if there is some sort of inspection database that somebody came and looked at the bridge and recorded some values, we wanted to be able to pick up the data from the inspections and visualize it in some ways. And so we found the NBI database, and in that database we found information for different types of performance evaluation and inspection. And we were able to connect to the database for specific regions and pull out this data and show sort of historical plots, as well as if there are any pictures that have been taken from that area of the bridge. If they are available and stored somewhere, we can also pull them in, and you can visualize them in this virtual environment. So the idea would be that a user of the system can pull out a particular bridge, build a virtualized model or virtual model of this bridge like this, and then go to the relevant databases and pull out the relevant information about the bridge that was collected over time, and visualize it there as well. And so you could kind of do virtual inspection of these structures in your office. All right, so but then the other question was, how can we connect this with real-time data? And actually, where do we get that real-time data? And what is that real-time data? What is it that we could potentially collect? And then if we have some sort of data that comes in about the bridge load, for example, how can we use the data to not only visualize something, but also to model the performance of the structure? And maybe have some sort of prediction analysis conducted as part of this virtual model, or this digital twin model, so that engineers can get some ideas about what to expect from these bridges. So in order to do that, we started to look at how bridges are tested, but more specifically, we started to look at how these tests are done in the lab environment. And we were lucky the Professor Andreas' team was preparing to run yet another test of a beam in the lab, and so we decided that we would really like to collect the data during the test and build digital twin model of that beam and learn something from how to integrate the data that comes from this sort of tests, but also understand what the data is and how we can use it in our digital twin model for bridges in general, and what else we can do with this data to sort of drive the modeling and simulation tests. And so this test took place just a little bit more over a month ago, I think. And this is the stress test where a weight is applied to, or load is applied to this large beam, and the beam eventually gets sort of bended, and eventually cracks develop, and eventually it collapses. And so we set up additional set of cameras so we can collect some data from this experiment, in addition to the data that is already collected by the team. And if we can then use this data to be reflected in our virtual model. So the data that is collected from our point of view, the data from cameras, and so we can extract quite a bit from there. And then there is also other types of data that were collected by the team that could also be used for other purposes. And eventually, we were able to build a virtual model of the beam in our environment that looks like this. This is sort of a simplified version of the test environment, but the beam actually has all the main characteristics of the actual physical beam here. And so there is this virtual load which is applied to it, and there is a deformation that happens here. And so here, let me go to the next slide. So there is an animation somewhere here. Let me see if it will work. Yeah, there's supposed to be animation. I don't see it's playing, but maybe it will start playing a bit later. So the idea here is that as the load is applied, then there is a deformation, and then a user can actually see as a function of time how much load is applied, what are the readings of the sensors, and as well as see pictures that were taken. So we were taking pictures every 30 seconds. So at any given moment of time, you can see how the actual structure of this beam will look like. And so through this, we were able to then enable essentially to navigate in the time, so the operator or the user of the system can actually go back in time to see what happened before and go forward in time. And so this model is there, and it is working now. Yeah. So yeah, here we go. So there is this animation that just started. That, as you can see, as time goes by and the load is applied, there are some deformations and there are pictures which correspond to that, and so on. Now, So this is just a visual representation, and so we very quickly understood that, of course, the accuracy of this is just there is some visual resemblance, but it doesn't mean that this deformation happens exactly like it's shown here. So we started to look into how we can actually model this with finite element analysis tools. So one of our students built a model for this bridge, or for this beam, and then started to apply some forces in a particular location and model this to sort of reproduce the process of the actual deformation in this virtual environment, and then export all these geometries from this tool into our Omniverse environment, so we can actually visualize what really happens there more precisely and more accurately, so we can build a more accurate bending model. So the simulation was done in Abacus, and then the geometry was exported into ParaView, and then from the ParaView, with the help of plugins available in Omniverse, we were able to bring this geometry back into this virtual environment. Now, of course, there are some aspects of this that are still somewhat problematic. For example, this finite element method simulations, depending on the accuracy required, are time consuming, so we do not necessarily can run all of this in real time or in the times that the time frames that we are interested in. So there is some more work to be done to get this to work faster. But anyway, so we could bring the actual physics-based simulations into our virtual environment as well, and be able to sort of simulate performance of these structures and visualize this performance in this environment. We also look at the cracks. So we built some software that would take pictures that were collected from these experiments, and would then extract the cracks from these pictures and would superimpose these cracks on the geometry of these virtual beams. And so here you can see, for example, where those cracks are starting to form. Now, what we've done here, we basically took just one-time snapshot where these cracks were well developed. This summer, we want to go back and re-evaluate this a little bit more and build the software that can extract, or models actually, perhaps machine learning models, that can extract these cracks from the moment they start to form during the experiment. And so we can actually measure the thickness of cracks, their length, and perhaps something about their geometries from the beginning of the experiment, and sort of compute how these cracks behave with higher loads. And so our idea here is that given the load, we want to get some sort of a model, some sort of an idea how these cracks can be created, but also given the cracks, so taking a picture of an existing beam, we also want to get some ideas about how much load there must have been applied to the beam so that this particular type of cracks formed. So we want to kind of use this data to develop models to study this phenomenon both ways. So I guess there is an animation somewhere here as well. Yeah, these animations are pretty heavy. Yeah, and so we've been also working on developing this software. So we started to apply some machine learning models that can be used to extract cracks from pictures that look like this. And then, this is not exactly precise yet. We need to spend more time on developing this software. But nevertheless, we are sort of able to extract bigger cracks relatively accurately, and we are able to superimpose these cracks on top of these geometries in our Omniverse environment, and so that they can be visualized. And our goal is eventually to get this to be visualized essentially in real time as this experiment continues. So, so with that, this is what we have done. We investigated different technologies needed to build this sort of virtual models or digital twin models of precast concrete bridges, and we identified the challenges as well as opportunities in building this sort of models and what they can be used for. So our plans for this summer are to process the data set that we have collected in this past experiment, and sort of build a data set where for each of the pictures that we collected, we can also get all of the measurements of all of the forces that were applied to the beam and any sort of other descriptive information that is available there, so that we can establish a connection between the crack propagation and the amount of load applied to, and then try to build models for this. And also, we are interested in spending more time on sort of improving the performance of finite element analysis methods. Perhaps we can look at running these methods, running these computations on a high-performance computing system, so that we can get results much faster. And so we could, for example, run a finite element analysis model during the time of this beam test, and if we can predict accurately in real time what is going to happen to the beam, and also be able to visualize this in real time, so that users can observe virtual experiment in the digital twin model environment while the actual real experiment is taking place, together with the analysis and prediction that is computed on the computer. And ultimately, we are interested in connecting this with real observed data from actual bridges, and understanding how this technology can be used, for example, by inspectors and bridge engineers to, for example, evaluate the performance of the bridge, understand what to expect from this bridge as a function of time and as a function of load applied to it, without leaving their office. Just being able to use data collected in the field together with the simulations and analysis, detailed analysis, to basically predict what will happen. So with that, I think this is it for my presentation.
Thank you, Vlad, so much. I really appreciate the great work you are doing in the presentation. We have a few minutes for questions. I think I saw Samer posting a question. Samer, feel free to go ahead and ask your question, please.
Yes, thank you, Bassem. Great presentations, very nice topic that I'm always very getting interested to it. The cost of collecting the data to update the models in the digital twin is an additional cost for the DOTs. How the benefits of digital twin will offset these costs? Because it does seem that little cracks that needs to be monitored on an annual basis through footage or videos needs to be collected periodically. Would the normal way of inspecting bridges might be a lot cheaper than digital twin? And what's the benefit of it then?
Yeah, I think so. Let me try to address that. I think the idea is that with the simulation tools, it should be possible to collect this data less frequently, and simply run computational models to predict what might happen. I think the idea would be that if we have accurate enough models, given a snapshot of the bridge taken at one point of time, we can run different if-else scenarios to see, for example, if there is so much load on the bridge, then this is what will happen. If there is less load, then this is what will happen. And ultimately, given inspectors a more precise time when they need to do additional analysis, manual data collection. I think that will be the biggest benefit, that they don't have to. They will have a much better indication when new data needs to be collected or when new inspection needs to be conducted based on the simulations.
Thank you.
Okay, thank you so much for the questions, Samer. Any other questions for Vlad here?
I have a question.
Go ahead, Bob, please.
In reality, when you have a bridge, the drivers are dependent, when they are driving their car over the bridge, most often they may not be aware of what's happening on the bridge. So rather than knowing the cracking condition, if we rather know that how much load it can carry ahead after the cracking, that will be more informative to the drivers. That's what my feeling is. I am not expert in this, but my general feeling is to predict that how much load it can take at any point in time. So the future prediction of the loading capacity on that thing will be the more important thing than just modeling it over here.
Well, that's a very interesting comment indeed. If you could kind of run some sort of analysis
Yes.
and say, you know, from this point during this season, for example, this is the maximum load that should be applied.
Yes.
Yeah, I think that's very interesting. I don't think I didn't think about this application, but that's definitely a very interesting application of this. Yeah, absolutely.
Okay, thank you.
Thank you, Barbara. Other questions or Vlad? Okay, well, thank you so much, Vlad. Appreciate it. Let's move to the second presentation. We have our speaker for the second talk is Professor Guoqiang Li. Professor Li received his bachelor's, master's, and PhD degrees from Hebei University of Technology, Beijing University of Technology, and Southeast University, respectively, all in civil engineering. He received his postdoc training in mechanical engineering at LSU. He is currently the Major Morris S. Date A. Anderson Memorial Alumni Professor and holder of the John W. Ray Jr. Professorship in Engineering in the Department of Mechanical and Industrial Engineering at LSU. His research interests in the broad area of engineering materials, manufacturing, and engineering mechanics. And Professor Lee is going to talk to us today about polymer reinforced shape memory polymer rebars. Professor Lee, go ahead, please.
All right. Good afternoon. Can you hear me?
Yes.
Yes.
Okay, great. Good afternoon, everybody. And it's a pleasure to have this opportunity to share with you our research on the fiber reinforced shape memory polymer rebars. And today I would like to talk about several things. The first one is that the background, why we do this type of research, and then the ideas. After that, we talk about how we enhance the properties of shape memory polymers, and also show you several models that we did so far and trying to increase the deformability of the fiber bundles. Okay, background. You know that fiber reinforced polymer or FRP rebars has been used in repair, rehabilitation, reinforcement, and reconstruction of concrete structures. I know in the literature, people also call it 4R. Okay, so we know the advantage of FRP is that they're lighter and they're also corrosion resistance. And we believe that the FRP rebars can be further improved by using smart polymers. So here we are talking about the shape memory polymers. Okay. So what's the idea? You can see that here the above photo here is a FRP rebar using conventional polymer that we prepared in the lab. Okay, this is glass fiber reinforced. So the new idea is that assuming you have this rebar, what you do is that you do a tension programming, similar to pre-stressing in the concrete industry. Okay, so after this pre-stretching, you put into a concrete beam. Okay, and then this beam will be in service. Assuming during service, you create such a crack due to the bending, okay, or other type of stress. So now, by trigger the shape recovery process, because remember, this initial length of the rebar, this after the pre-stressing. So when the shape memory effect is triggered, this longer rebar trying to go back to the original length, which means that the rebar trying to shrink. When it shrinks, it will bring the crack in touch, or at least narrow the crack. So in such a way, the rebar not as a loading carrying device, but also as a functional device to help close cracks. If the cement concrete is self-healable, and then the crack can be self-healed. Okay, so there's a major idea. Of course, you can also prepare a smart rebar. Let's say it's a curved shape. And then you can do a compression programming. It becomes straight bar. And then you embed into the concrete beams. So later, when you're trying to the straight rebar will trying to bend back if you apply a negative moment to the concrete beams. So in such a way, you also can either narrow or fully close the crack. So this is the idea. Of course, you can see that in order to bring the fractured concrete in touch, you have to have enough recovery force. Okay, or the pre-stressed rebar must be able to output enough energy. So which will depend on the energy storage capability of the smart polymer. Okay, so how the polymer storage energy? So basically there are two mechanisms. The first one is this figure in the left-hand side. You can see that it's mainly through the entropy change. During the pre-stressing process, the polymer network will be aligned along a certain direction. Okay, this is a figure showing that. You can see this initial random configuration. So after stretch, it becomes ordered so that the entropy is reduced. Okay, so of course, entropy reduction will be able to store a certain amount of energy. So later when you trigger the shape recovery, so basically the entropy will increase and the ordered molecular structure will going back. So you will see the shape recovery. Another mechanism is enthalpy storage. So basically this one is through the chemical bond length change and bond angle change. Okay, if you recall the Gibbs free energy equation, you will see that, of course, both entropy and enthalpy will be able to contribute energy storage. Okay, so actually, we rely more on the enthalpy storage. The reason is that in the past, people basically rely on entropy, and the recovery force is or the stress is very, very limited. Okay, so basically, we propose the idea of enthalpy storage, and then we start to make new polymer networks. Here, show you one of them. Okay, so basically, this cross-linker and this monomer, when they have these chemical cross-links, will be able to make a new thermoset shipper polymer. And here we are showing the recovery stress testing. And you can see that after about 6% of a tensile programming or tensile pre-stressing, and we will have about 5 MPa recover stress. Okay, if you just depends on the entropy storage, this stress storage will usually be less than 1 MPa. Okay. So we also trying to see that if this idea is universal or not. So basically what we did is that we use dynamic molecular simulation, and then we also use solid mechanism modeling, and we compare a modeling result with the experimental result. We found that yes, look at this idea is correct. The bond length change and bond angle change indeed can storage the input energy. All right, once we know this idea works, we want to find more polymers and to see that if we can have higher energy storage and energy output. So here we show you one of the polymer. So basically here we show that for this polymer, we use different curing conditions. Let's say 100 degrees Celsius for 1 hour, for 1 hour plus 150 for 30 minutes, 100 degrees for 1 hour, 150 for 1 hour. Okay, you can see the difference in terms of the fracture strength and also the difference in terms of the ultimate tensile stress. So based on this one, definitely you can see that this current condition seems give us a little bit higher tensile failure strain, and also the tensile stress is not that low. Okay, so the DSC test result showing that the glass transition temperature is about 130 degrees Celsius, which should be proper, for the infrastructure use. Okay, once we know we have a good polymer, the other side is that we try to find a good matchable fibers. Okay, as you already know that for lots of synthetic fiber like glass fibers, carbon fibers, their tensile fracture strength is very low. For example, glass fibers usually about 3 to 5%, they will fracture. Okay, you can see that in order to input more energy, the fiber during the pre-stressing process, it cannot be fractured. So in such a way, we're trying to see that can we further increase the fiber bundle fracture strength? Okay, so if you just do the straight fibers, of course, you have no way to change it because it's a material property, right? So we're trying to see if you change the configuration of the fibers. Okay, so here you see that we have two bundles. One is straight fiber bundle, another is a helical configuration. And then we did finite element modeling, and we try to compare. So here is the normal stress comparison. So basically you can see the normal stress in the helical fiber is 66 times lower than the straight fibers. So definitely this is a good sign, right? The stress is smaller. And then if you compare the shear stress, of course, these helical fiber bundles will have a much, much higher, 98% times higher than the straight fibers, which definitely is understandable, okay? And then if you compare the maximum, the principal stress, and again, this time the helical fiber is 7 times lower than the straight fibers. Again, this is a good sign to use this new configuration, okay? And how about the principal strain? Okay, the principal strain is that the helical fiber is about 44 times higher than the straight fibers. So that means this fiber bundle will be able to deform more. Recall, our polymer can be deformed 10% before it fractures, and glass fiber for straight fibers 5%. So now, by just changing the configuration, you'll be able to increase the deform ability so that the glass fiber bundle will be able to match the smart polymer. So hopefully they will work together to be able to store more input energy. Okay, of course, here is compared to the shear strain. Understandably, the shear strain, of course, the helical fiber will be much higher, okay? And the principal strain, again, okay, 68% higher in the helical fiber than the straight fibers. Okay, recently, after attending this workshop last month, so we trying to see that if we can further change the fiber bundle configuration, for example, breeding the fiber rovings into some patterns, for example, this pattern, as compared with the straight fiber pattern. So actually today, this morning, we have the first modeling result. The result showing that you compare the longitudinal tensile stress, you can see that for the braided fibers, everything the same. Okay, the same loading, same boundary conditions, same materials. The maximum tensile stress is about 1.5 times lower than the straight fibers. Okay, again, this is something very, very deserve expectation. Okay. And here is a maximum principal stress. And of course, we have not done the straight fibers, so we cannot compare with straight fiber. But my expectation is that the principal stress for the braided fiber bundles will be lower than the straight fibers. Okay, so is a displacement. Okay, and again, I expect the braid fiber bundle will have a larger displacement so that they will match the smart polymer matrix. Okay. Very good. So again, by this morning, we have a preliminary test result. Okay, so here you can see that these are braided bundles. Okay, so braided bundles, and then we have the epoxy at the clamps, so that we was able to clamp into MTS machine to do some tensile testing. Okay, here is a close look of the braided fiber, and here is after the tensile testing. And this figure showing that these are the straight fibers after the tensile fracture. So all the two samples are made with the same 3 rovings of glass fibers. And this figure shows the test result. For the braided fibers, the maximum tensile force is 1,269 newtons, and the fracture strength 5%. And for straight fibers, and the fracture strength is 4.97%, and the maximum load is 1,168. So means what? Just based on this one sample test result, of course, we cannot make a solid conclusion because we need more samples to test. However, just based on this one, you can see that the braid fibers showing a little bit higher deformability, but also a little bit higher load carrying capacity. So our next stage study in the summer will be focused on more configurations and do more of testing, and also trying to convert these fiber bundles into real rebars. Okay, I thank the support by the TRANS-IPIC and also the graduate students involved, Ali and Winston. And that's all. Any questions?
Thank you so much. Great presentation. Any questions for Professor Li? Any question? I have a few minutes.
Ask a question.
Yeah, go ahead, Pinar.
So great, very interesting presentation. Thank you. So how would the fact that this reinforcement will go into concrete and it will be, bounded, the fibers will be bonded to concrete, and also will be confined by concrete. Would that affect the expected behavior? I know you haven't gotten that far, but just as a guess.
Yes, just the expectation. I think before I go to that step, the first question we need to solve actually is the interfacial bonding. Interfacial bonding between the FRP rebar and also the concrete. Because usually they have a thermoset polymer have very, very poor interfacial bonding. So that's why you see that when we prepare the conventional polymer-based FRP rebar, this one, so basically we're trying to, make some grooves, trying to improve the surface roughness so that they have some interlocking with concrete. Okay, so as for your real question, will that affect the behavior of the concrete? So this is something that we need careful study. And for example, when the rebar recovers, right? So let's say we have 5% recovery strength, okay? But the concrete, during this recovery process, the concrete may subject to some tensile stress, okay? Will the concrete survive this tensile or not? This definitely is a question and need to be answered. So I hope that once we were able to prepare this type of rebar and do some small scale testing, will be better to answer this question. And of course, our final goal is trying to make a larger scale rebars and do some real larger scale concrete beams and to test it. However, I do believe that your question is very, very important. And I will keep this in mind. One, interfacial bonding. Another one, during the recovery process, will this type of shrinkage cause further fracture in the concrete, for example? Thank you.
Thank you, Dr. Li.
Dr. Li, I have a question.
Okay.
I observed that in helical design, it can bear more stress but I believe there must be some kind of angular relationship where at which angle it will be at the maximum stretch.
Yes, yes, definitely. That is very, very important. You change the angles, you change, for example, the helical type of fracture, and also the braided, right? For the braided, for example, you have so many different ways to do it. So these are all something that, we will trying to do the modeling in the summer. So we will create more patterns. And for the helicals, of course, the helical angle will play a very, very important role for the stress distribution and also the fracture of the bundles.
Okay, d'accord.
Yeah.
Any other questions?
Okay.
Well, one thing I have just a comment that not really a question, just something for you to think about in terms of the actual level of force that you need to do actual pre-stressing in any of the bridge girders that we typically use. So just keep this in mind. I know that the focus here will be getting the recovery stress from the resin itself, not from the fibers. The fibers really don't do much, and correct me if I'm wrong, in terms of producing the recovery stress. So, so the volumetric ratio of the fibers with respect to the resin will play a big role in the amount of force really you are able to establish coming from, the resin itself. So it would be, one comment is just to look into realistic pre-stressing force levels that we use in beams and how much material it takes from these shape memory polymer bars to be able to produce something close to that, or if not, then what would be the typical application for these new types of shape memory polymer bars? Just something for you to. I know you're very early still in this research, and we're in the exploratory phase, but just something to think about for future steps.
Yes, I fully agree. So definitely this part probably need to come from you guys. Okay, so if I have a crack, assuming a reinforced concrete beams is fractured, cracked, and based on the distribution of crack and opening the crack, and you can tell me that if you trying to apply a recovery force, how much force you need, and then we can consider how much, for example, the dimension of the rebars, and also if we can find that type of polymer to have the type of recovery stress. And the best combination, of course, will be the shape memory alloy fibers and also the shape memory polymer matrix, right? These two shape recovery material combined together probably can do something very good. However, the thing is that it's a cost. And also the weight will be much heavier than what we are talking about now.
Right. Yeah, that's a very good point you make, Dr. Li. I know one of the things we look at the steel strands, for example, which is of course different, direction of the research, but we're looking at something in the range of 30, 40 kips, 1,000 pounds, that each one of these strands, just a single strand, is able to produce in the concrete. So this is the level of pre-stressing force that the industry looks into now and is using right now. Just to give you a little bit an idea, and we could talk more about that, obviously, and exchange ideas about the level of force that we really need in actual applications. But very, very good and promising direction of research. No question about it.
I think that will be very, very useful for this research. If I know the level of force needed, and then we'll be able to, to design the type of rebars towards that requirement. Or it may never, meet that requirement. At least we have a clear goal to achieve.
Okay.
Yeah.
Thank you.
Thank you. Good question.
Any final question for Dr. Li? Okay, well, with that, thank you all for attending today's webinar. as I said, we'll be reaching out to you soon with the schedule for the next webinar. Chris will be communicating with you all that, and we wish you all great summer, start of the summer. I know that, I hope you have good, enjoyable time, yet also productive summer. And feel free to reach out if you have any ideas, any questions, or anything related to TRANS-IPIC or the work you're doing with us. And we always want to hear about the good work that you are doing, whether it's educational, research, or anything else. Thank you all, and have a great rest of the day. Thanks. Bye-bye.
Thank you. Bye-bye.
Bye-bye.
Bye. Thanks, everybody.
Bye.